Friends, so in previous video we have seen various simulators like Aspen Plus, Aspen Isis, ChemCAD and all others listed here, and I say that they are more or less similar in their performance. However, they differ in terms of their number and type of components, like the type of components they deal with: hydrocarbons, organics, inorganics, solids, like thermodynamic models and solvers they have, like whether they have all the activity coefficient models which you like, or equation of state, or various specifically modified equation of state to take care of some specific species or specific components. Unit operations they can handle, whether you can add your own code, you can add other language and add it to the simulator. You can link your simulator to other simulator and vice versa. And naturally, as I told in the last few seconds of the video, that user interface of the simulator, user interface should be something which a person who is using should get a feel of it, should get feel that he is working with some process engineering. It should look like flow sheet which we are drawing on our pen and paper, using pen and paper. So user interface, yes, also makes a important aspects when you want to evaluate this kind of simulators. So based on this, you can evaluate them. And if we talk about some survey which was done some 20 years back, which is more or less prevalent today as well, is that how the market share of the simulators are there used in undergraduate courses, and you can see that most of the chunk is divided between ICs and Aspen Plus, and now since Aspen Plus and Aspen ICs are same, you can see that overall scenario is more than 50%. In fact, there are so many others which have come into picture, but they are very marginally able to introduce get into the academic field. When there was a question raised to teachers that why were they not using simulators, some important thing came up is that there was a lack of awareness of learning these packages. There was a common misconception that if I try to learn a specific simulator, it will take too long. However, that's not the case. And there was no motivation for the faculty members to use simulators in the classroom to explain the things. In fact, now there are so many animations and simulations available for various courses that if a teacher uses it, it can really supplement the knowledge sharing between a teacher and a student. However, out of all this, what experience says is that even if you break this barrier and you learn a simulator, going through various seminars and workshops and all other things, you don't use it often. So you learn it once and then you forget it. So if you don't put it into practice, these simulators are of no use. So as a teacher, I should be able to use it in whatever course I'm using to explain certain things, and these simulators can be very good training tools. They are in fact being used in industry to train the operators. They are being used in OTS, operator training. Simulations are already available, but these simulators can be used very wisely and very properly. As a student, your job is to learn one simulator and try to use it to understand various topics, various things of various courses which you have studied in chemical engineering. Now coming to the structure of a simulator, now this is a typical kind of simulator which I am considering. I am considering it as a modular mode of a simulator, and there you have a classically you have a component database. You have various compounds, as I mentioned: solids, hydrocarbons, non-hydrocarbons, organics, inorganics, and various kind of compounds, and they are constant. So that makes a basic foundation of a simulator. More the compounds, more the constants, naturally better is a simulator. Then a thermodynamic model solver. So all the compounds needs thermodynamic property estimation, so that requires various models. So from pure component properties to the mixture property, enthalpy, entropy, and whatnot, and phase equilibrium like vapor pressure and vapor liquid equilibrium. And when you go to reaction, it can be reaction equilibrium constant. For all these things, you require gas free energy of formation, heat of formation. All this data would be stored in the simulator, and if the data is not there, you should be in a position, like simulator should be in a position to estimate them. So this all comes under thermodynamic model solver. And this two layer that makes a simple simulator and a process simulator different. This two makes a simulator a process simulator, because when you take up this, that really makes it to a process engineering problem. So this is where your process simulators will be having this database and this thermodynamic model solver inbuilt into its library, so you don't need to do it separately. Like if you are using MATLAB maybe or Excel, you have to do, suppose vapor pressure is to be calculated, you have to make a separate code, you have to separately calculate it and then feed it to the Excel. Whereas here you just need to supply temperature and vapor pressure will be there in front of you. So that makes a difference between a simulator and a process simulator. So thermodynamic model solver is the second layer. Third layer is a flow sheet builder. So you have to generate a flow sheet, you have to pass on the information from one block to other block, right? So that makes a flow sheet builder. So this flow sheet builder is a very integral part of any particular modular mode simulator. We'll discuss what is modular mode as we proceed further, but this is by and large, this is something which is very much being used in industry and academics. That's why I have considered this as a structure. Then there is a unit block solver. A unit can be a distillation column, it can be a separator, it can be a heat exchanger, it can be a mixture, it can be only a stream, whatever. So there is a unit, and for every unit there are certain equations, material balance and energy balance equations. So they are already built into the simulator. You don't need to write separately. You just have to use plug and play when you go to process simulator. So all those material balance, energy balance equations and all the equations associated with that unit block would be there in that. But that unit should be present in the simulator. So fourth component is a unit block solver. Fifth one would be data output generator. So once the simulation is done, you want to generate the data. Whether the data you want in terms of a graph, in terms of a table with specific number of properties, specific units is what a user has to do. And then a flow sheet solver. So if the flow sheet is a bit complex, you need to advise simulator that this is how it should be solved. So that control is to be supplied from a user. Maybe in some of the flow sheets you want a specific constraint to be followed, like you want your mole fraction to be less than 1 or greater than 0, or maybe you want your pressure to be greater than 0, or you want your temperature to be maximum to be this. All such constraint you can put, and that is what comes under the flow sheet control. So this by and large makes any process simulator. And there will be something here and there, addition, deletion, but then by and large the structure of a model mode process simulator is this. Then let us talk something about the process simulation, and then we'll wind up this particular video. And that is, it was used in both industry and academics, but initially it was used only for design purpose, not for no other role. All other courses were not touching simulation. However, now the things has changed because it has got a large database. It can have physical property estimation, so you can use almost in every particular course. You can use it in fluid flow, you can use it in heat transfer to explain what is happening within the particular process. So you can see the effect of one variable on the other variables, and all those things are added, and as we proceed further you'll be able to see that. So now process simulation is an integral part of chemical engineering. Like you cannot have a course of chemical engineering without a process simulation. And it took up after 1970s, but most importantly what you have to learn as a chemical engineer is simulate with understanding. But I have seen so many students relying upon simulators like anything, but you have to understand that the chemical engineering is sitting on the other side of the screen and not inside the screen, right? Because whatever it provides, you have to analyze. There is a rule in computer terminology: garbage in, garbage out. So if you don't give proper input, it will not give you proper output. Sometimes even giving proper input doesn't give you proper output because of one or other reason. So you have to analyze, you have to interpret the results of a process simulator. Don't blindly rely on process simulator results. Yeah, it won't give you completely wrong information. So for very simple things it will always give you correct results as long as your inputs are proper. But don't blindly rely for a key solutions. Always analyze the results. So I think this is it for today's videos, and we'll discuss further when we meet next time about what a simulation is and where it will be helpful in process and chemical engineering. Thank you.